Hey, hi everyone. Very good evening. Hi Harsh. Hi Anil. Good evening. Hi Srisha. Good evening. All right. So is my voice is clear to you all? Is my voice is loud and clear to everyone? Perfect. Great. So let's do a quick recap on the topics we have covered yesterday. So what are the topics we have covered in yesterday's session? And if I give an any task, what is that? You can just post it on the chat box. I'll take a look at it. What are the topics we have covered in the last session? So Anil, Leanet, AlexNet networks and implementation. Perfect. Leanet, AlexNet 5. Task is to try to download PyCharm, right? Yes, Harsh. Anil, regarding perfect. The handwritten and mission printable characters. Wonderful. Perfect. Yes. To explore dropout. Yeah, dropout. Have you all researched about it? Dropout. Have you all researched about it? I think I've asked you to go and explore dropout. So Harsh read some articles. What about others? No one? Okay. All right, so let's get into today's topic then. So today we are going to get into, I think the last session I spoke about something called as transfer learning. Try to complete that daily given task so that maybe it would be very much helpful for you. So Lean at 5 yesterday we discussed, and AlexNet we discussed. And we have discussed, we just looked onto the name, something called as transfer learning yesterday. So again, we will get into what is this transfer learning concept. I said we will again look into this. What is this transfer learning? How exactly we are going to use this transfer learning? We will be understanding it today with respect to two networks. One is Vg16 and the other one is Vg19. So how we are, how this transfer learning is going to get used. So today we will be understanding that particular part. And also, one more thing, 1 minute. So dropout, okay, only hash. This techniques consist of turning off neurons with predict. But this means that every iteration using a different sample of the model parameters, which forces each neuron to have more robust features that can be used with other random neurons. However, dropout also increases the training time needed for the model's convergency. Perfect, Harsh, that's right. So you understood what exactly dropout will do? Have you understood? Not fully. All right. Maybe I think only one exploded. Because of that, since at least one exploded, I'll let you know what exactly this dropout function is all about. So with that, we can get started. I expected at least few of you would be doing that, but at least this is much little bit disappointed. So, but it's fine. So we'll understand how exactly this dropout function will work, and then we will get into this transfer learning concept. That is how exactly this transfer learning we can do with respect to two architectures, that is Vg16 and Vg19. That's what I mentioned it here. So that's what we will be looking into it today's session. All right. So let me share the screen. So this is the agenda we have. So Vg16, Vg19 architecture we'll understand, and this transfer learning concept script and also transfer learning script of transfer learning, we look into it. And here, if you see, there is something called as parameter and hyperparameter. So that's nothing but hyperparameter calculation. How exactly this parameter calculation we need to do? That also we will just take one network and we will try to understand what are the numbers, how many parameters one model is having. So this will decode and we'll try to understand. And with that, we will be winding up our today's session. All right. So let me do a quick recap on this deep learning part, what we studied. So we understood the difference between deep learning and machine learning. Deep learning deals with unstructured data sets and also structured data sets. So we understood all the different optimizers, different loss functions, and different activation functions we learned. And then we got into this particular theory, that is, we picked up one data set, MNIST data set, and we tried to explore it. And then we discussed about CNN architecture, the major limitation with respect to only one feed-forward network. It is not doing a pretty good job. So we need to extract as many features as possible, and then we need to give it to the feed-forward network for the prediction. That is doing a pretty good job. So then we discussed about yesterday we discussed about this Lean at 5 and AlexNet architecture, pretty old model. But after this AlexNet model, it became a big hype in the market, because from after 2013, even this AlexNet is having a concept called this dropout function. So now let me start from that particular dropout function, and then the next architecture which got released by Google is nothing but Vg16, and again they released another model, Vg19. So these two architecture we will be understanding it. This dropout function, as I mentioned, it's today is going to be very much useful for overcoming this overfitting problem. What is that overfitting problem and everything? Let's understand this. So let me open the file which we worked yesterday. 1 minute. So So yesterday we worked on lean at 5. Lean at 5. What about model's performance? Okay, this is how it learned. Now what I'll do, let me again execute it. Now I'm adding one layer called as, going to add one layer called as dropout. Padding. Normalization. Yes, that's what overfitting problem. Okay, so when we are training this, what I'm doing. So after this particular part, average pooling, convo and everything. So here, after this is where my fully connected layer is. So I'm going to add, first let me import one more layers, comma, in this particular keras.layers. Here, one more layer, I'm just going to add, comma, there is something called as dropout. I'm just going to, let me import it again. And this network here, I'm just going to add model.add, add this dropout layer. What exactly to do? Applies dropout to the input. That is, the dropout layer randomly sets input units to 0 with the frequency of rate and everything. Now we can just take a read about this later. But rate was given. Rate is equal to float value between 0 to 1. Fraction of the input units to be dropped. Okay, fraction of the inputs unit to be dropped. So let me change this. Rate is equal to, let me give 30% of the input need to be dropped. All right. And yeah, so after flattening also, let me just do it. Model.add dropout rate is equal to 0.3. Where is it? Sequential. Okay. Fine. So RMS block. Let me again retrain my model. But again, this will take some time. So what I'll do, let me open my Colab quickly. This is the architecture. Let me open the same file as today. We can't say irrelevant data. That's not the right term, Harsh here. So what I'll do. So this is not the one. Let me go with this particular case itself. That is the older script. Untitled 10. I think this is the file which we worked yesterday. Right. So runtime, GPU fine. Click on connect. Okay, let me comma drop out. I think it is O small, I think so. Sorry, D is small. For this, okay, D is capital, O small. Fine. D drop out. Fine. Then let me load this. Load my data set. This one, execute it. Yes, and after flattening it, model.add dropout 0.30% of the neuron. The same thing, let me add it after this layer. Let me now execute it. Now let me keep the same thing. Now let me train it for 15 iterations. After this, I'll go for evaluation. Let me copy. Let's go, let me paste it. After this, I'll go for prediction. My prediction, everything, I don't know. So just the model performance, copy, paste it. Create a new cell, paste it. All right, so let's wait for a while. And let's compare yesterday how this one was so much noisy. That is, my training loss was showing more noisier. And even see this, the training loss started from more than 100%, and it almost reached 80%. But sorry, the test loss, training loss almost reached zero. We are expecting to reach zero, but the training loss is very high, and also more fluctuations. Now I included, but see this. This is what overfitting problem. Let me explain what is this overfitting. So what is this? So what we are trying to achieve is nothing but loss should be equal to zero, right? Loss should be equal to zero. So this blue color is nothing but what? Training loss. So the training time loss is zero, but what about the test time? The loss is maybe 80%. So training time error is zero, test time error is 80%. So now my model, did it learn well? What do you say, everyone? It learned well, but we can say it memorized. Instead of learning, it memorized the particular patterns for the provided data, it memorized it. But if I'm just giving any new data set, it is unable to give us the perfect result, the way how it got learned. Maybe we can think of it in this way. It's an engineering time. Even though we are having 6 months time, only few are going to utilize the time very well. But most of us, what we try to do is nothing but only before 2 days examination, we try to take 5 chapters and we try to make a Xerox copy of a local author, and we try to distribute within our friend circle. Okay, each person one chapter, they will study it, and even after studying, even that one chapter will get shared among our friends, and that's how we used to study and directly show it to the examination. Yes or no? And in case if you just if you don't understand any particular problem statement, you will just simply memorize it, even if you're not trying, even if you do not understand the particular problem. So you just go and memorize it. And if you see a similar kind of question in your examination, without even noticing this particular numbers and everything, we just try to expect the same answer what we have already memorized. Yes or no? How many of you have experienced this? How many of you have gone through this kind of experience? All right, Jyoti. I think you are a topper, I think so. Okay, fine. So the point here is nothing but the training time, the error is zero, but the test time error is very high. Now this one, if the test also, if it is just reaching towards at least close to zero, I'm pretty much fine with it. Able to get my point, what I'm trying to say? If the test error, if it is equal to zero, sorry, if the train error, if it is equal to zero, my test error should also be equal to zero. Yes or no, everyone? Harsh Jagdish Jyoti. Perfect. So now let me just try to see what exactly is happening here. Clear it. Let me come back here. Okay, here also it had happened. The training had happened here. Now what I'll do, let me just come back here. Now let me execute this. Now I just include a dropout. Now look onto it. See how exactly now the performance is. So here if you see, the training loss is also 0. The test loss is also 0. Now in the similar way, in the earlier case, here if you look onto it, the training, blue color is nothing but the training accuracy. It reached almost to 95%. If training accuracy, if it is 95%, what should be the test data accuracy? What should be the test data accuracy? It should be also 95, around 95%, right? When the number of iterations is increasing, right? When the number of iterations increasing, the test data also, it need to show the similar kind of experience, right? So now let me execute this, the test accuracy, look onto it. Blue color is my training error, and it almost reached the same accuracy. Now, if you go for this evaluation, earlier it had given 77% accuracy, 81% loss. Now, if you evaluate it, the loss is 0.03, accuracy is 99%. It's all because of this dropout layer. All right, by using this dropout layer, we are overcoming this overfitting problem. Now, the next question. So what does dropout really do? All right. So dropout, what exactly it is trying to do is nothing but, see this. Let me speak about only this neural network. What exactly it is trying to do is nothing but, see this. Now, in my, I'm flattening it. After flattening it, how many neurons I'm having in this particular flattened layer? I'm scrolling down. Okay, let us take a look at it. So only fully connected layer. So this is where my fully connected layer starts from. You can give this dropout only to this fully connected layer, not anywhere. So after flattening it, this 120 neurons, so that is going to be my inputs, right? So my input layer is nothing but my 120 neurons will be there in my input layer. All right. Now I've just given dropout. Dropout is nothing but 30%. Okay, let me explain this dropout layer. Hidden layer is this one. So hidden layer 1 is nothing but 84 neurons. 84 neurons. And then dropout I'll explain. And then the last one is softmax, that is output layer, where I'm having 10 neurons over here. Now there is an interconnectivity between this. Each and every neuron, I'm connecting everything. All right, I'm connecting everything. Now what exactly this dropout, I've just given dropout in between. Here dropout is 30%. 30%. What exactly it means? So now here you're having this 120, all your important pixels, right? 120 pixel values you're having. Each and every pixel is going to have that 120 pixel. Now when I'm just forward propagating in time, 30% of the neurons from your input layer will be automatically deactivated. For example, this neuron will get deactivated, this neuron will get deactivated, this neuron will get deactivated. So 30% of your neurons from your input layer will get deactivated, and now it will move on to the hidden layer. With the remaining 70% of the cells, it is going to get into the next hidden layer. Now this again, I'm saying hidden layer. Now I wanted to pass every neuron to the other cell. Now again, I've included 30% of the dropout function. Again, what is going to do? Randomly, 30% of the neurons is going to become inactive. Now I forward propagate, and I'll just calculate the weights and biases. I compute the loss function over here. Now again, I'm going to back propagate. When I'm again going to forward propagate in time, again 30% of the neurons will get deactivated, but this time randomly, every time, maybe this time, what will happen is nothing but this neuron will get activated, this neuron will get deactivated. So in this way, and again, this neuron will get deactivated, this neuron will get activated. So in this way, what I'm doing, I'm just doing it for again and again. I'm making sure every time I'm not allowing my network to carry all this pixels. So in this way, what is happening? I'm just subjecting the output layer. Hey, these are all the important features. Now learn it. So I'm not giving the complete picture to my network. In one iteration, I'm just providing only a small picture to my network, but to learn, this is number 5, this is number 10. And again, for backward propagate, again, I may take the same picture, but again, some other important feature, it is learning it. So instead of providing the complete picture to learn, because for the training data, it is 100%, but for the test data, there are the variance may be increased. So to overcome that kind of problem for the test data set, during the training time itself, what I'm doing, I'm deactivating 30% of the neurons from the input layer and the hidden layer, and I'm just feed forwarding the neural network. When I'm backward propagating, again randomly the neurons which got deactivated the previous time may get active, and the neurons which was active the previous time will be deactivated. And in this way, and again the second hidden layer, in this way, it will get repeated again and again and again, so that this overfitting problem is going to be reduced. Got it? Right, Jyoti. It learns through partial information, correct? Why we are allowing partial information? Because when I'm supplying full information, training error is 100%. Training error is 0. But when I'm providing a new data, it is not like that. So when I'm in the learning process itself, I'm providing partial information. With that, but we can't say partial, yes, partial information, but again, we are giving a complete picture to the training data by providing new features every time. That's what the point. So what will be the Jagadish, sir, what will be the effect of if we increase dropout to 50% or reduce to 10? So it's again a hyperparameter. Hyperparameter is nothing but trial and error. We have to check it out. 30% it's doing a good job. Maybe you can try with 40 or 50%. But if you give more, maybe underfitting. Yes, underfitting will happen. Underfitting is nothing but the training error. It will be very poor. So we don't try to do that. So try to keep it less than 50. So that should be great. Even 40 also we can do. But 30% and 40% depends on the number of neurons. Here you're having it. Here it is 84. So 30% of the neurons, if I'm removing it, you can just think of how many neurons I'm trying to make it deactive. Got my point? Try to keep it less than 50%. Maybe the 0.3 or 0.2 should be something fine. Is this point understandable, everyone? Just confirming. Okay. All right. So this dropout function, great case. This dropout layer has been introduced from this, not this LeanNet. LeanNet, they did not introduce this. Imagenet architecture, what as an architecture wise we are looked on to yesterday. That's the same point which I mentioned in the yesterday's theory. If you see, this dropout has been introduced by Imagenet architecture itself. Okay, so let me not give it, but just for the purpose of understanding, in case if you're constructing your own network, I have not given it to this convo average pooling. That's there, it is not required. So here we try to give it after flattening it. So after flattening, then here itself it become an input layer. Only at the feed forward network, we try to keep this dropout function. Okay, so that's how we try to optimize our network performance by using normalization process, by using dropout function. So in this way, again, we do have a lot of other methods as well. But dropout is very much important to overcome this overfitting problem. All right. Perfect. Now let's get into the next process. That is, what is this? Let's get into one topic called as transfer learning. Okay, what is this transfer learning concept? It's nothing but, so today most of the deep learning algorithms or the automation is happening with respect to this transfer learning concept. Now, what is this transfer learning concept? Even what I'm doing here as a trainer, I'm doing transfer learning. Now, what is the transfer learning? The intelligence, whatever I've acquired in my mind, I'm transferring that intelligence to you. So transfer learning, so that you all can learn it. In the similar way, so here with respect to LeanNet and AlexNet, we constructed our architecture from the scratch, right? And for model training and everything, And imagine for AlexNet architecture, how many parameters is going to include, and the time duration for executing AlexNet architecture to be pretty high. So we need the GPUs, high-end GPUs, we need it. So that kind of power, do we have it in our CPUs? No, we don't have it. Now what I'm doing, so this kind of architecture has already been built, and it's been built on top of another data set. That is, there is one competition called as, let me get into Google. That's it. ExcelR CV competition. That is image. Yes, so there is one competition which will have an Imagenet competition. That is, yes, Harsh. So what is this Imagenet competition? If you read it, the Imagenet large-scale visual recognition challenge is a benchmark in object category classification and detection on hundreds of object categories and millions of images. The challenge has been run annually from 2010 to present, attracting participants from more than 50 institutions. So this AlexNet architecture has won at 2012. This architecture won this Imagenet competition by 2012. Now, what is this Imagenet challenge is all about? See this, who won this 2012? AlexNet architecture is the winner of this Imagenet large-scale visual recognition competition, okay, which is classification competition. Imagenet is a data set of over 15 million labeled high-resolution images with around 22,000 categories already. So, and maybe who created Imagenet data set? So if in this way, there are a lot of things, but how exactly this Imagenet data set is all about? See this Imagenet data set. Imagenet. I think you got an understanding about what is this Imagenet. Imagenet competition. Now, what is this Imagenet data set? If you see, what is an Imagenet data set? The Imagenet data set contains 14,197,122 annotated images according to the wordlet hierarchy. Since 2010, this data set is used in the large Imagenet this particular challenge, a benchmark in image classification, image detection. So, what is an Imagenet? Imagenet is nothing but is used for is a large data set for annotated photographs intended for computer vision research. The goal of developing the data set was to provide a resource to promote the research and development of improved methods for computer vision. Now, this data set is nothing but they have already collected, see this, they have already collected millions of images and they stored it into this particular Imagenet database. Okay, so this particular, in case if you wanted to download this database, it's possible. You can just download it. So in this way, they collected images of cat, dog, and everything. See this particular way they have collected, and it's basically 1,000 class classification. Imagine for one class for 5 class classification we have done with respect to CNN network. So for 5 class classification, if you wanted to build up a best network, at least for one class, we need to have 25 to 30 different images. Let me repeat it. So we just worked on CNN architecture, where I asked you to go and collect images from 5 different people. And one person, let's say if I'm just asking, I wanted to collect Jyoti's image, I would need at least 25 to 30 different images. So for 5 people, you can just 5 multiplied by 30, it's nothing but 150 images. Now here it is 1,000 class classification. So how many neurons I have to keep it at the output layer? 1,000 neurons I have to calculate it. Sorry, 1,000 neurons I have to keep it. So if that's the way, imagine how many images I have to collect it. So if I'm collecting that many number of images, the processing power, your CPU is not at all sufficient. So we have to go for higher processing powers. So with respect to AlexNet, they trained it for a longer period of time. I think they trained it for 2 weeks. And this AlexNet won this particular challenge. But again, they wanted to reduce the training time. They wanted to achieve the result more quickly for this 1,000 classification. The next year challenge. So in this way, the network's computation time, it need to be reduced, but accuracy wise also, we are not ready to compromise. So able to get my point? What I'm saying, able to get it? Jyoti and Harsh, got it. Fine. So for that purpose, keeping that in their mind, so Google came up with the next architecture, which is called as Vg16. Great, Jagdish, which is called as Vg16. Now let me share this Vg16 architecture. Let's take a look at it. So see this Vg16 and Vg19. It was introduced by around 2014, developed by a group of researchers from the University of Oxford. So about Vg16, VGG or the pre-trained object recognition model, it consists of 13 convolutional layer, 5 max pooling layer, and 3 fully connected layer. And this is about the Vg16, and we'll understand it in some time. Now what we will do, let's try to take a look at this Vg16 architecture. Our Vg16 architecture will look like this one. See this is what the theory of dropout, how exactly dropout will look like and everything. And yep, just take a look at it. Vg16 architecture is nothing but I would be having an input image, and then I will use conva, 2 conva, max pooling layer, 2 conva, max pooling layer, 3 conva, max pooling layer, 3 conva, max pooling layer, 3 conva, max pooling layer, and then 3 fully connected layer. Just try to count how many layers I have. 1, 2. Don't try to include max pooling. Except max pooling, how many layers I have? Just try to count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So totally you're having 16 such layers, which is having weights and biases. All right. So because of this max pooling layer, it will never have weights and biases. All right. So weights and biases, nothing but each and every layer internally, because conva is a weight matrix. If it's a weight matrix, weights, it is having weight matrix, and internally it is having one bias as well. So 2 conva, 2 and 2, 4, 3 conva, 7, 3 conva, 10, 3 conva, 13, and then, sorry, 3 conva, think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, yeah, 14, 15, 16. So because of this reason, we are calling it Vg16. Now the next architecture, again, the research is nothing but Vg19. It's nothing but 2 conva, 2 conva. Here we have kept 3 conva. Now it is 4 conva. Here again, they have kept 3 conva. In Vg90, they have kept 4 conva. 3 conva. Here I have kept it 4 conva. So just we are adding 3 more layers, right? 1, 2, and the third layer. So we are just naming it as Vg19. So this is how Vg16 and 19 architecture will look like. So, but if you wanted to construct it manually, it will take a lot of time, right? So we can construct it, but are we able to, can we process this? See this, it is having 64 such filters in the first layer. Maybe let me zoom a bit. 64 such filters in the first layer, and then 128 filters in the second 2 conva it is having. The third 3 consecutive convas, 256 such filters, and then 512 filters, and then 512 filters. So can we process this thing in our local machine? What do you say? Are we able to process this? Processing power. We need high-end GPU machines again, right? So again, the problem is we need high-end GPU machines. All right. Now, but this again, Vg16 and 19 won at 2014 basically. Now let's construct it. So instead of constructing from the beginning, now what new thing they came up with is nothing but they came up with one concept called as transfer learning. Now, what is this transfer learning? Just take a read on this particular part. Transfer learning is nothing but deploying VGG from scratch on a large-scale data set is tiresome and computationally expensive task due to the depth and number of fully connected layers nodes of the model's architecture. Another challenge is that building VGG from scratch requires considerably large memory space and bandwidth, since the size of the Imagenet trained VG16 weights is 528 MB. Instead of building VGG from scratch, we can perform transfer learning concept. That is, utilizing the knowledge like weights and features of the previously trained models to solve a similar kind of problem. The inputs to the input layer is removed, and our data set is passed as input, and output layer is also customized. So this is what all about transfer learning is all about. So this Vg16 has been trained on that Imagenet data set for 1000 class classification. If you look onto it, what is the how many neurons I have it? 1000. So this architecture specifically has been constructed for handling Imagenet data set. Now I wanted to solve my own problem. So what do I do is nothing but I'm just going to cut off this input layer, and output layer I'm just going to remove it. I take the weights and biases, whatever got trained. I need that weights because weights is nothing but what all this calculation I'll be having better weights. That I take it and I just give my input image. With that best weights, my network is going to outperform it. So that is the concept of transfer learning. So now what we will do, let's take a look at how exactly this will work. See this pre-trained script. Let's take a look at it. And from this VGG, see this. Screen I'm sharing with you. Let me share the screen. Just a while. This one. So what I'm just doing is nothing but let me just get into Keras. Keras.io. Click on Get Started. Keras API reference. And then here, if you see Keras applications, let me click on it. Now, if you see Vg16, Vg19, these are all nothing but my pre-trained models. Okay, let me click on Vg16 if I want to how to make use of it. So tensorflow.keras.applications.vg16, this is how I have to call it. And the default input size of this model is 224 by 224. That's what this particular process. Note, each Keras application expresses a specific kind of input processing for Vg16 call tf.keras.applications.vg16.pre-processing input on your inputs before passing them to the model. Vg16.pre-processing input will convert the images to RGB to BG. This we can take a lead on it later. Now what I'm doing is nothing but first I wanted to import it. So see this, let me create maybe, I think this should be understandable. So from Keras applications.vg19, that is, here you're having it, right? Here you're having this particular part, tf.keras.applications vg16. We have to import this particular vg16 model. So what I'm doing, so from keras.applications.vg16, let me give it vg16, import vg16. Make sure your runtime is written GPU. Okay, GPU. Click on connect. Because already one, since this was in GPU, right? So now I can't take 2 GPU machines, only one thing I can get it. So let me terminate it and close. Let me connect it again. So from keras.applications.vg16, how exactly I'm getting it? This is a Keras application, Keras Keras applications, and then I'm just wanted this particular VG16, and within this VG16 I'm importing this capital VGG. Look onto this particular terms. Now let me execute it. Now this VG, after importing it, I'm just storing into something called as model. Jesus. This is in case if you try to do it in your local machine, it will take a lot of time. And if you look onto it, .h5 file, the weights, it internally has the weights and biases. Okay. Now we are not going to create anything from scratch. already whenever you're calling, hey, I want Vg16, that's it. This model with the weights.h5 file is got created. Now in the earlier case also we just tried it. So we created our own network, right? We created our own network. And what we have done finally, we have taken it as a .h5 file, right? So this, what exactly it is having in .h5 file? It's nothing but the weights and biases I'm having it. So the researchers, they have constructed this network and they exported this particular .h5 file and they made it, given it to this particular website. Now, whenever I'm calling, hey, I want Vg16, that Vg16 model, I will be getting in my hand. Now I take it in case I wanted to see what is the model. So if you see model.summary, I'll be able to see what exactly the model is. So I'm getting 224 by 224 by 3 is nothing but RGB image, then 2 convo layer, max pooling layer, 2 convo layer, max pooling layer, 3 convo layer, max pooling layer. I'm getting a summary, 3 convo layer, max pooling layer, 3 convo layer, max pooling layer, and then flatten it. Then 2 fully connected layers, and it is going for 10 class classification. All right, this is my model summary. Now what I'm doing, model is done. Now I wanted to test one image, how exactly it is doing. So what I'm doing, so again, from keras.preprocessing.load image, I wanted to load one particular image, and I wanted to pre-process my images as well. That is converting into arrays and everything. All right, let me just use it. So now, with respect to this load image, let me load one image from internet. Maybe let's say cat or I think dog. Click on dog. Let me take any variety of dog. Maybe this one. So there are a lot of dog varieties, right? So this one, let me take a copy. Even faces towards that side. But anyway, let's save images. Okay, it's not HFL. I just wanted to have an JPEG. To save it in. Okay, now it is JPG. To come back, let me click on upload. Let me click on copy this path. Let me keep it over here. All right. See, this target size is nothing but 224 by 224. I'm just giving it. This image has been loaded here, and I'm just converting into an array format. And then by using this image again, I'm just reshaping it. That one is nothing but I'm sending only one image. How many images you are trying to send? I'm just sending only one image, because if you look onto this is expecting how many images. Or you're sending how many images we are sending it. So we have to specify. So I'm going to send one image. Image.shape 0. One is nothing but what? What is shape 0? Is 224, comma 224. Shape 2 is nothing but it is 3. Right, so that's what this particular image shape is all about. Now if you check it, 1 comma 224 224 by 3, that's nothing but the image. Now I'm just going to pre-process it. Pre-processing my image, reshape it, and pre-process it. And if you want to see how exactly it got pre-processed, you can just take a look at it, or in the other way how we have done yesterday, that also we can do. Now model dot predict my particular image. The result got stored over here. It is applying its weights and biases. I have not constructed my model anything from the scratch. I'm just testing how exactly Vg16 is performing. Now I got the result. Now let me look onto the output. From keras to Vg16 pre-process and also decode predictions. Now the prediction answer is nothing but it is something numbers. Right? It is just giving me all this 1000 class classification. It is so the output neurons, 1000 class, 1000 outputs I'm having it. So now I'm just decoding this particular predictions, and I'm just giving this part. I just wanted to have the labels. Now if you see, now it is giving the top 5 suggestions. So 79% probability is just going for Labrador Retriever. So there are different types of dogs. So let me copy and how exactly this dog is, right? So is this, let me just check some images of Labrador Retriever. You can't do it. This is a very similar image, right? The same image. Got my point, everyone. Now, if you see, I have not trained my model from the scratch. So, but I'm just testing this particular model, its weights and everything by providing a new image, how exactly it is performing. Up to this clear, everyone? Able to get my point? All right. Now, but the thing is, okay, this model got trained for Imagenet data set, but this model need to be applied for my data. So how do I need to apply for my data is nothing, but I have to fine tune this particular model. I don't need to train it from the scratch, but I wanted to fine tune this particular model so that it is going to behave well. So what I'm just going to do, how to fine tune this particular model. Let me give you one small template to you all. So if you're following this particular template, definitely it will be working for all your pre-trained models. So now see this. Let me share it. So if you look onto this particular part, CNN architecture's template it is. So for all from this Vg16, all your other models, every model is a transfer learning concept. You don't need to concept from the scratch. All right. So, but I'm having my data in my Google Drive. All right. See this. All right. Here, if you look onto it, I'm having within my train data, I have 4 folders. Within each and every folders, I'm having some images. Okay, I'm having some images. I'm having, this is my own image, but I don't need to train my data from the scratch. So what I'm doing, all your Google files will get stored into your Google Drive itself. If you see collab notebook. So this file name is CN architectures, right? So if you find it here, there will be something called a CN architectures. You can find it. Same for multi-class classification. All your scripts is Untitled 10, which I just opened it. So everything it will be saved in your, by default, it will be saved in your collab, drive itself. It will basically create something called as collab notebooks, and within that it will get saved. Okay, let me just click on it. So now I'm just into this particular part, that is transfer learning CNN. Let me click on it. So where exactly I'm having some train data set and also test data set for the testing purpose. Okay, I'm having some data, right? Now, firstly, we have to import this drive into this Google Colab. So for that, what you can do, let me click on this. So here you can find something called as mount drive option. All right. See this, run this cell to mount drive. So automatically, if you click on it, you will be getting this kind of script. Let me click on a shift enter. See this permission, this notebook to access your Google Drive files. Let me connect on Google this. So if it is for the first time, maybe it will ask you this kind of details. So which one you want to do and everything. You click on it, run allow. And it will now it will just show me one link to take okay, mounted. In case for you, maybe you will be having one link to click on it. You need to go to that link, copy that authorization code or everything and paste it here and click on enter. It will be done. Now for me, I've already tried it multiple times. I'm not getting it, but it says mounted at content drive. So once this is a refresh button, let me click on refresh. Now I got this drive. So my drive has been included or imported over here. Now from this, I can just provide the path. Now what I'm just trying to do is nothing but let me just see this. These are all the packages to download. Keras, keras.mod sequential, Conva, model, keras.models, I'm importing model, pre-processing images. This is image data generator so that I can just mention the path. Shift enter. Now from keras applications.vg16, let's say I'm importing vg16. Now, if you get into this keras.io, get started, there are small configurations, slight tweaking you have to do. Keras API reference, Keras applications. Let's say I wanted to use this Vg16 as a pre-trained model. Now here, if you see, include is equal to top. What exactly include is equal to top? Whether to include the 3 fully connected layers at the top of the network or not. So these things I slightly need to modify. So what I'm doing, I'm saying include underscore top is equal to false, which means that, hey, I don't want whether to include 3 fully connected layers at the top of the network or not. I don't want my top layers. Okay, the 3 fully connected layers, whichever you're having at the last, means top of the layer is nothing but 4096 neurons what you created. I don't want that. So I'm just removing that particular fully connected layer. So if that's the case, learning itself is not going to happen. The learning will happen only if you're having dense layers. So now I'm just removing that particular dense layer. That is one point. And the next point here, if you see, class is equal to how many class classification it is? 1000 class classification. Now, how many class I wanted to go for classification? 4 or 5. This need to be slightly tweaked. Other than that, everything need to be everything need to be there. And weights is nothing but Imagenet weights. That's the same weights I'm going to take it. That's weights and bias I'm going to take it. So I'm not going Imagenet weights, and input shape is nothing but 224 by 224 by 3. That's the default one. Input shape, if you wanted to give it, even if it is none, if you read it, input shape is nothing but has to be 224 by 224 by 3. That's the same thing, right? Now let me import it. This is a one tweaking which I'm trying to do. And also I'm saying don't train existing weights. That is, I don't want it to, I'm having conva, max pooling, conva, max pooling. I don't want to, when I'm sending an image, again, it should not go through conva, max pooling. It need to go through, but again, it should not get trained with that conva, max pooling. Feature extraction don't need to happen. Already, I provided my image that is from the image data set. My image, if I'm just passing it anyway, it is going to be very similar to that. So because only it's all about feature extraction, right? So feature extraction, image, object is going to be at the center or the right corner or whatever it is. Already I'm having my weights and biases. So what I'm doing for layer in this VGG underscore layers, I'm just saying layers dot trainable is equal to false. That is, I don't want to train it anything. I don't want to train anything. All right, I just wanted to make use of this weights. So I'm just making is equal to false. Now what I'm doing, I'm just flattening it. In the output layer, I'm just flattening it. And I'm just saying that, hey, I just wanted to my output layer. All right, or layers, you can add more if you wanted. Now, after flattening it, I'm just looking onto this particular X variable, I'm just giving it. So this is going to be my input. And then what I'm doing to that, dense layer is nothing but the last layer. I'm just saying, hey, I want 6 neurons. All right, only 6 neurons, the last layer. And then I'm using this particular activation function, a softmax activation function, and then I'm using this particular X. Once try to execute it, you should be able to get it. Now, finally, let me click on Shift Enter. And then create your model object. So here, if you see, by using this particular part, keras.models, I've imported something called as model. Now I'm using model. Inputs is equal to this VGG. What is your input and what is your output? You have to give it. VGG underscore model dot input. So that is nothing but my inputs. I'm going to pass it over here. And output is nothing but this is my output layer. That is 6 neurons I'm having in my output layer. I'm just giving it over here. And finally, I'm just looking into this particular model dot summary. This is 224 by 224, the same thing. But if you look onto the output, dense layer is nothing but flatten. All right, flatten, and directly I'm just giving it to my dense layer. Now I'm just combining, compiling it with respect to Adam, and the loss function, I'm just choosing it up. And with respect to image data generator, I'm providing my where exactly my train data path. My train data path is within this. Let me click on it. Colab notebooks, and I'm having this transfer learning. This is my train data. So click on it, copy path, I'm giving it. And that is the path which I just pasted it here. Or on the target size is 224 by 224 by 3. And again, the tested data set path also I'm just giving it here. And it says what is the shape of it. And then model dot fit, I'm fitting my model. And then I'm just saving it as an output file if you want it, because this is the H5 file which got trained for my data. So this .h5 file will be used for 5 class or 4 class classification, I think so. So whichever the model, this H5 file will hand over this to my clients. Now, if you see, for our data set, this will get trained, and this will just say, earlier I just had this particular file, that's what it's giving me. And then if you wanted to check it out, you can just check it out with respect to this particular script. Able to get an idea, everyone? This is a slight tweaking that you're trying to do it over here. That's it. Able to get an idea? What are the small changes? All right. In the similar way, all right, in the similar way, you're having Vg19. So all the models, whatever it's mentioned here, it's a pre-trained model. Let's say I wanted to make use of something called as ResNet 50. Click on it. So where exactly it is coming from? TF KRAS application ResNet. So what you have to do, what are the small changes? So instead of this ResNet, small ResNet, right? So come back here. See this, you just need to do, see this, from KRAS applications, then port ResNet 50. And the remaining architectures are the same thing. Let's say you wanted to use this transfer learning of Inception Net. Where exactly, let's say mobile net you want to do. Let me click on mobile net. How exactly to do it? Again, small mobile net, but you have to import M and N. So again, come back here. So import it and make the remaining, include top layer is equal to false and follow the same architecture. It should be working for everyone. All right. So this is the common template that we can follow if you wanted to make use of any other architectures here. All right. I'll just share the script with you all. Just one try to use it out. So the point is why we are coming up with a lot of pre-trained models is nothing but if you see the size of this Vg16 and 19 is 528 MB, 549 MB. So the size is pretty high. Now, with respect to the other architectures, if it is an A program, I will be speaking about other architectures as well with ExcelR. But I've already, it means we are already learning a lot of steps here. So in the similar way, how we are doing Vg16 and 19, if it is ResNet 50, one new factor will include it. If it is Inception version 3, again a new concept. There is something called skip connections and a lot of new stuff which will be including it with respect to each and every layer. But the major point is nothing but I wanted to reduce the size of my network. If you see this ResNet 50 98, and also if you look onto the accuracy wise, where exactly the accuracy, top one accuracy for this is high. It is 92% accuracy. All right, 92% accuracy. Here it is 90% accuracy. So the network sizes got reduced. Accuracy wise also got increased. Number of parameters, if you see, here 138.4 million parameters. Here it's only 25.6 million parameters. So when we wanted to come up with the new architectures and use it for the transfer learning concept, it need to be lightweighted. Keeping in the mind that, hey, I want to go with a lightweighted model. Accuracy wise also need to be increased and parameters also need to be reduced, because if I'm having more parameters, so it is going to be like more calculations, more computation time it is going to happen. So having that thing in their mind, so people are coming and participating with their new architectures. If you look onto let's say the other architectures, if you get into a program, I can just share you these files and everything. So there is another architecture like this. So this architecture is for Inception Net architecture, and ResNet architecture will look like this. Architecture of ResNet. This is a skipgram technique, and other architectures like Inception module and everything. Call it. I'm not getting into this more, but the point is, people are coming as participants or who wanted to participate in this competition. If their architecture, if it is getting selected, it will be listed. It will be listed here. All right, it will be listed here. Still, see this. Still, this is on progress, so it will be listed over here, and people are coming up with new architectures every time. Every year they are just coming up with. And now, if you see AlexNet and LeanNet, it is not even listed because that's a very old model. Now, from 2014, whatever the models got released, it's getting listed with respect to KRAS applications. If you scroll down, you can see how less the model is. See this number of parameters is 5.3, accuracy wise is 5.3 million, 93% 3. So with less number of parameters, are we able to increase the level of accuracy and efficiency? That's what the point is all about. Got it, everyone? Perfect. So this is all about this Vg16 architecture on 19. And we just learned about how this transfer learning concept is all about. Now the next point, after we can take a break now, and post break we will come back and we will just learn one topic, that is, if you look onto this particular part that is here, where is that? Yes. So what is this parameters? I said weights and biases. How exactly it is getting calculated, weights and biases. What are these numbers are? We will just understand it, okay? And how exactly this numbers 138.4 it is coming in, and this particular part, what is this particular number is coming in? Because if I'm able to understand this architecture well, we will understand why. We will understand even more better that what are this parameter concept is all about. We will be getting it. So that part we will touch it post break, and we will wind up our decision. Okay. All right. So how many minutes would you like to take a break? 5, 6, 7? You can choose one. Okay, 5.5. There is no option, Harsh. Like Jyoti, no break. Okay, I think interested to learn more. Okay, let me take a break. Then 5 minutes break. Let me just go for a quick break, and let's come back by 8:19, and we can continue. All right, let's go for a quick break. Hi everyone, it's all back from break. Jyoti, Jagdish. Okay, perfect. Now we understood what is this transfer learning concept is all about. We started from understanding dropout, how it is going to going to help us to overcome this overfitting problem. And then we learned about this Vg16 and 19 architecture and how exactly we can make use of this transfer learning concept we learned it. Now we are moving on to the next one, that is parameter calculations. Okay, how to do this parameter calculations. Let's try to, how it is already done. We'll understand this. Okay, let me share one screen now. Just give me a minute, everyone. Okay, take it out. Yes, here it is. Let me open my blackboard. All right, let me share my screen. All right. So let's understand from here. All right. So this is a linear architecture. Okay. Um, Basically, let's go with this. Let me increase it. All right. Hope it is visible. Now let us go with this. See this. This is my layer, and the output shape of that particular layer. Number of parameters got involved. Now, what is this number of parameters? Is nothing but at this particular layer, how many weights and biases got involved? That's what we call it as the parameters. Okay, just observe this here. Now, what I'm having. Firstly, input layer, right? So the input layer is nothing but input shape is 28 by 28 by 1. So the input layer, the output shape is also 28 by 28 by 1. Input layer, there is no weights and biases. So secondly, again, after this input layer, it is going through conva. So we know that input image going through conva, max pooling, sorry, average pooling, conva, average pooling, flatten, dense layer, dense layer, dense layer. We know how to construct this particular architecture. Now, this input layer here I just given 28 by 28, but according to the architecture it is 32 by 32. But let's go with this particular flow to understand this particular calculation. Now input image shape is 28 by 28 by 1. Okay. Now this is going through convert 2D of size 5 by 5, and let's go with, and padding is equal to valid. All right. Now what would be the resultant size? If padding is equal to valid is nothing, but we know it is 24 by 24, right? We already have done this particular part. But let's do this kind of calculation. How exact it is 156 So here, if you see, how many convo layers I have it here? 6 layers of convo. So for kernel size is 5 by 5. So for one convo, how many, what 5 by 5, right? So 5 by 5 weights I have it. Let me write it down. So for one convo, that's it, 5 by 5 is equal to 26, correct? Sorry, 25. Plus, that is, you're taking your input image. Let me just write it like this. You're taking your input image, and you're multiplying with 5 by 5 kernel. So this kernel will have how many biases? So whenever we are constructing our neural network like this, this is one node, right? So bias, each and every neuron is going to have one bias, correct? The similar way, here, I'm just going to construct one 5 by 5 kernel. So it is nothing but 25 such weights I have, and one bias also will be belong to this weights, right? So one. In this way, how many such filters I'm creating? It's 6. So 5 by 5 and one bias. 5 by 5, one bias. So one kernel size of 5 by 5 is having 26 weights and biases. So 26 multiplied by 5 is how much? Sorry, multiplied by 6 is how much? Because 6 such kernels I have. 26, one convoy is having 25 weights because 5 by 5 is 25, plus one is nothing but bias. In this way, I'm having 5 convoys. So 26 by 6 is nothing but what? 156, right? So that 156, I got it over here. That's the number of parameters. All right. Then let's move on to the next one. So average pooling layer. Does this average pooling layer, is it going to have any weights and biases? Pooling layer, is it going to have any weights and biases? No, no weight. Just it is going to go with the matrix size of 2 by 2 and strides 2. Just it is going to pick up the average value. That's what it will try to do. No weights and bias calculation is going to happening over there. So because of that, here, number of parameters involved in this average pooling layer is 0. Okay. Now, second the conva. So 5 by 5. So now one 5 by 5 is going to have 25 plus 1 bias. That is nothing but 26 weights and biases I have. So 26 multiplied by how many such filters I'm creating? It's 16. So 26 multiplied by 16 is how much? 26 multiplied by 16. It is 416, right? So this one will be of size. Sorry, it is, I just mentioned 2. It is not 2. It is 416 basically. All right, it is 416. Right. Now again, I'm just flattening it and sending it to this. See this, for average pooling layer, I don't have this particular, 1 minute. I think we are missing something. So 16 such layers, 5 by 5, 4, 16. There is one calculation, is it right or wrong? 1 minute. So I think this part I have not done this before. Let us take a look at this network, that is Vg16. That is basically 2146. One calculation we are missing it. Just give me a minute. So here I've just done it for Vg16. Let me take a quick look at it. All right, I got this. So the point is, All right. See this, you will be getting it. All right. So this part, let's come back after some time. So let's look at this particular Vg16 since this calculation has already been done. So you can just take a look at it. See this. Now this is my Vg16 network. All right. This is my Vg16 network. Where exactly? Conva, Conva. Just observe this. Input layer, Conva, Conva max pooling, Conva, Canva max pooling. And then I will be using 3 Conva max pooling, and then 3 Conva max pooling, and then again 3 Conva max pooling, and then flatten it, and then 3 dense layers. I'll be having it over here. All right. Now, let me come back here. And then after this, let's compare AlexNet also. So input layer image size is nothing but 224 by 224 by 3. Input layer does not involve any number of parameters. Now Conva 2D. What is a Conva 2D of size? See this Conva 2D, I'm just trying to give a filter of 64 such filters according to the network. Look at this particular network. 64 such filters I wanted to create it. So the output of Conva 2D is nothing but 224 by 224 by 64. Now we want to calculate for number of parameters. This part we already know. So for one Conva layer, that size is 3 by 3, 3 by 3 Conva. So 3 by 3 multiplied by 3. This part we missed it earlier. Multiplied by 3 is nothing but 3 by 3 Conva need to be multiplied by this 3. Why? Because 3 such depth I have it in my network. All right. Because 3 by 3, it need to apply for red color channel, and behind it green color channel, and behind it blue color channel. So finally, this 3 by 3 multiplied by 3 channels plus 1. This is for one bias, I'll be having it. So for one Conva layer, I'm having 28 weights and biases. So in this way, I'm having 64 such filters at the first layer. So what would I do? 64 filters, 28 multiplied by 64 is 1792. All right, right, 1792. So I'll be having 1792 for the number of parameters for this first Conva. The second Conva is nothing but again 3 by 3 of 64 filters, the same answer, right? But now 3 by 3 multiplied by 64 is nothing. See this 3 by 3, that such Conva need to be multiplied by 64 such filters, because behind this, the previous output, we are having 64 such depth. So that depth we have not included in the earlier case, but actually the depth also need to be included here. So if you are multiplying there by 6, you will be getting the answer. Now I think you got the clue. So 3 by 3, this Conva need to be multiplied with 64 depth. So for one Conva with need to be multiplied by 64 depth, I would be having 577 weights and biases. So for 64 such filters, because of this, sorry, here at this layer you're having 64, you'll be having 577 multiplied by 64 is 36920. So for this second Conva, the number of till here, the number of parameters got involved is nothing but 3692. Sorry, not till here, only for this calculation. Now max pooling layer that does not come up with any weights and biases, so 0. The third Conva is nothing but Conva 2D. So this third one, all this particular Conva is having 3 by 3, 3 by 3, and but now the 128 filters I'm doing it, but how the calculation need to be made? So this 3 by 3 multiplied by previous layer is 64 layers I'm having. So 3 by 3 multiplied by 64 plus 1 is 577. So in this way, I'm having 128 such filters I'm having in my network. So 3 by, if I'm having 577 for one Conva, 577 multiplied by 128 is 73,856 I'll be having. So for the third Conva layer, I'm the number of parameters got involved is 73,856. And for the fourth one, I'm having the same thing, 128. So again, what will happen? For one Conva, 3 by 3 need to be multiplied with 128 the previous layers depth. So for one Conva, I'm getting 1153. So this 1153 need to be multiplied with 128 depth for this particular layer. So 147,584. So that would be the figure. Again, 2 Conva max pooling, 2 Conva max pooling is done. Now max pooling layer does not involve with weights and biases. Now we are going for the third layer of Conva, 3 consecutive Conva we are having it. So Conva 2D. Now if you see this size again 3 by 3, 3 by 3 need to be multiplied by 128. So 128 plus 1 if you do it, 3 by 3 multiplied by 128 plus 1, 1153. So this 1153 need to be multiplied with how many such filters at this layer? 256. So we do that, 29516. This is what you'll be getting it. So I'll be writing it over here. Now again, at this particular year, 3 by 3 multiplied by 256 plus 1. So what is the value? 2305. So this 2305 multiplied with 256. So 590080. So that would be the value. And again, the third layer. So here, what is this? Again, 3 by 3 multiplied by 512 plus 1. Sorry, at this particular layer, 3 by 3 multiplied by 256 plus 1. Same as this. So I'll be getting, because this is the same value, right? Because even these two things are same. 3 by 3 multiplied by 512 plus 1. And here also, since I'm having the same result, there's a number of parameter involved in the 9th layer and the 10th layer would be the same thing. So I'm getting it. Max pooling layer, no parameters. Now here, 3 by 3 multiplied by 512 plus 1. So for one conva, 2305, but the depth is nothing but 512. So when I'm multiplying this, 1180, 160, that's what I'll be getting it here. So I just mention it. Sorry, for one such conva, but 1180, where exactly this one mentioned? Yeah, so this is where we are. And now in this way, this one 3 by 3 multiplied by 512. All right, so in this way, you can just calculate it. And now finally, you'll be having the remaining 9. In this way, we'll be doing the calculation. Now we are going to the dense layer. Dense layer, see this? We flatten it because for max pooling, we don't have it, flatten it. Now dense layer, how many neurons we have to create? 4096 neuron we have to create it. So each 4096 neuron multiplied by the previous number of neurons is 25086 because it's weights, each and everything is weights. So every neuron here is going to have biases. So 4096 multiplied by 25088 plus 4096 if you do. So this will be the number that you'll be getting it. The next layer, that is a hidden layer 1, 4096 multiplied by the previous layer's number of neurons 4096 plus 4096 nothing but the bias of the current layer. So if you multiply it 16783, this would be the number. And finally, the output layer, 1000 neurons, 1000 multiplied by the previous number of neurons is 4096 plus this layer is having 1000 neurons, so 1000 biases I'm adding it, 4096. Finally, if you just add it up, the total number, it will be like 138, 357, 544. And that is the figure that we got it. Sorry, this is which one? This is not the screen. So we looked onto the other one. Pre-trained model. See this? 138, 357, 544. 138, 357, 544. So this is how the number of only I'm focused on weights and biases. So because of this, the total memory, if you look onto it, 138, right, which is nothing but 138 million. Now let me go back to the documentation. 138.4 million parameters. So this is what my weights and biases, I have to reduce it. So that is the reason we are going for some other networks like mobile and everything to reduce the number of weights and bias calculations. Getting an idea, everyone? Perfect. So this is what I meant by this chapter. That is where exactly this calculation. So here, if you see parameter and hyperparameter calculations. So this parameter calculation is this one. What I meant by hyperparameter here is nothing but when we are constructing our network, I told you to try changing this particular figure, right? So where is that? So where exactly here, if you look onto it, try changing this to, when we are constructing our network, try changing this to tan H and everything. And also if you see within this particular network, where is that? Here we are having, there is the screen. Yep. So here you're having dense layer, you're having something like, scroll down, you're having something called as kernel initializer, bias initializer. This is what we call as hyperparameters. Hyperparameters nothing but the parameters which we are having inside this kind of layers, we call it as hyperparameters. So from where exactly initialize for the bias vector, from where it is actually taking in. Again, go to keras.io. Get into this. Get started. Keras API reference. And here you're having layer API. Click on it. So layers API. So custom layers. So here I just wanted to know about, let me scroll down. These layer activations. Layer weight initializers. So you can initialize the weight from normal, random, normal plus. Let me click on it. Just take a read on it. So if you're just setting this kernel initializers and a bias initializer, so it can be random normal. What exact is random normal? Take a read on it. And random normal is nothing but initialize that because as I said before, weights and biases are random number. So random number can be, so what is the random number? From which distribution the random number is from? So it generates tensors, nothing but numbers with a mean of 0 and standard deviation of 0.05 from the normal distribution. That's what random normal is all about. And what is this random uniform? Generates tensors with the uniform distribution, where exactly the minimum value is minus 0.05 and maximum value is 0.05. So from this value, I would be getting random weights and random numbers as weights and biases. So the next one, truncated normal. What is truncated normal? Initialize that generates truncated normal with the mean of 0 and 0.05. Take a read on it. All right. So if you want to do it, so truncated normal, this is how we have to give it. And zeros. That generates tensors initializes 0. So all your weights, it will be 0 in case if you want to initialize that. Once, initialize to 1. All your weights and biases, it will be initialized to 1. And Glorot normal. So this Glorot normal initializer is also called a Xavier normal initializer. What exactly standard deviation is nothing but what? Square root of 2 divided by fan in plus fan out. What is this fan in and fan out? You can just take a read on it. In this way, this is what I meant by hyperparameter optimization. So what you can do is nothing but we can just open this and kernel initializer, just copy this and try changing it when you're constructing it. Kernel initializer is equal to in the single quotes. You can come back here. Let's say Glorot uniform, how to use this. Glorot uniform, maybe in this way. Glorot uniform, let me copy. We come back here. Let me paste it like Glorot uniform. In case if it is throwing an error, you can just see how exactly to use it. Let me see this. It got executed, not a problem. All right. So in this way, try tweaking this hyperparameter which is available in your network. Again, for why we have to do it? For model optimization. All right. Kernel initializer, we have bias initializer, we have a lot of other hyperparameters as well. This is what this chapter, parameter and hyperparameter, is all about. Parameter calculation we looked onto today. What is it hyperparameter is all about? I think we had an understanding what is it all about today. Got it, everyone? So your keras.io, keep that as a reference and try working on the other steps. It should be fine. All right. Great. So with that, we are winding up our within image, computer vision, we are winding up our image classification segment. So there are two segments within image classification. One is computer vision. One is image classification, and the other one is image detection, or we can say it's an object detection. So we are winding up this image classification now. That's all about this image classification. And now tomorrow we will get into image detection. So in one object, how we are able to detect multiple in one image or a video, how we are going to detect multiple objects. So that's what we will be looking into it tomorrow's session. So any questions till now? If there is no questions, can I get quick NQ or no doubts ND on the chat box? Yes, Amar. PyTorch is a framework, Amar. PyTorch is a framework like TensorFlow, Keras. All right. So hope there is no questions. All clear. Practice needed. Yes, Jyoti, right. Only practice will make you to have good understanding on this concept. Maybe it might seem clear, but when you're working on it, you will face a lot of errors and you will overcome that particular error. So that's how you will be learning it. Yes, Amul, we can use it. We can use it for image classification, for object detection. We can also use it. There is something you can read about YOLO algorithm. We might not get into that, but YOLO, behind that YOLO algorithm, this PyTorch is getting used. That particular framework, that's how they just defined it. Image classification and also image detection, we can use PyTorch. But the way how we write in PyTorch, the syntax or the way how it is going to be little bit different on how we are scripting now. So as I said, computer vision itself a very big subject. And if you wanted to get into computer vision specific area, we have to learn PyTorch. PyTorch framework will be very much useful. All right, but I'm not going to get into that. But with Python, yes, we can achieve image classifications and everything. But for even more better optimization, or if you wanted to get a good resolution and great classification, if it need to happen in real time, with respect to PyTorch framework, people are making it. I know one of my learners who she got selected in, she's from civil background, she got selected in one AI-based companies, and they asked her to work in Linux OS because that would perform a little bit faster compared to Windows. And also it's a computer vision based application. So she started learning PyTorch and everything. After learning this particular course, it completely depends on which kind of project you're working on, which project your company is working on. Based on that, we will be picking up the tool and we will be learning it. But the concepts, everything need to be clear. That the framework and the way how we are script, the framework and also the tool, everything, it's company dependent. What exactly they are saying, and also we should also give some suggestions to the clients as well with whatever we learned. And also once you get selected in your kind any company, they will also let you know which framework they are working, and accordingly we need to go and learn that and work on that particular tasks. It's not like whatever we are learning, yes, that's what it is getting used. But in case if they are saying that, hey, we are working on this tools, just can you learn it? Yes, we should be open to learn that and come back and work on it. Hope that makes sense. All right. That's it for today, everyone. Let's come back, meet at 7 o'clock tomorrow and continue our next session. Take care. Have a good night. See you there. Yes, Harsh. Good night. Good night, Shraddha. Yes, Jagdish. Take care. Bye. Yes, Dr. Lina.